Okay. So I would like today to devote the most of our time to the practical tasks, because for the moment, all of you are already have executed first practical task, that is a task devoted to the Fourier series. So all of you did this, but we need more, because according to our schedule, according to the syllabus of our discipline, I'm just trying to open it. Let's see. Yeah. We have actually 7 practical tasks, but we will see how it will work. For the moment, for today, I'm ready to explain you everything about practical task number 2 and number 3, because you have all the material, I mean theoretical material concerning this, so I think it not be so difficult and very reachable goal for you. In order to start my explanation, I will share my screen, and you see, do you see my screen? Yes?
Yes, doctor.
Okay, so here it is our syllabus, and here you can see practical works, and works number 1, 2, and 3 are estimated in maximum 5 points. So today we will try to finish with an explanation of these 3 practical work, concretely number 2 and number 3. Also, we have model control work, but I will prepare you for this control work a little bit later, because for the moment I would prefer just to be hurry with the practice. At our Google Classroom, you can find already, here is the main page of our Google Classroom, and here is the task. And we already completed practical task number 1. And the next one is practical task number 2. And here is a file attached, and I will open it right now. Again, at first you should know your number variant, and these numbers are the same as it was in practical work number 1. So for Ahmed is NV number of variant equal to 1, for Esteban 2, for Robert 3. Okay, and then what is the task? You have, you can see original function. Now I'm selecting it. Yes, can you see my selection, right?
Yes, doctor.
Okay, so x from n, this is an original discrete function that is defined by its totally 5 values. X from 0, it's the first value, x from 2, second one, x from 2 multiplied by 2, then x from 3 to 3t, and x from 4t. So totally n, the number of discrete values, is equal to 5. Of course, in real application and in real task, these numbers would be much better. Not better, but more than 5, of course, because if we operate with some real signals, let's say discrete signals, so in practice, number of discrete digits could be tens or maybe hundreds, and of course 5, it's not a real situation, but we have to be able to operate with the simplest, with a simple example, with a simple function, because the main things for you is just to understand how it works and what is the algorithm, what is the consequence of operations that you have to do. And if you will succeed with this for the very short and very simple function, so it will be enough for understanding. It will mean that you are already could use this tool, this mathematics, this method for the practical task. So you already know what does it mean and how it works. That's why I think that it would be enough, just 5 discrete digits, and you put here your values, and the values are depending of the number of variants. So x from 0, it's just nv, number of variant. I will make a little bit bigger. I think it's better. So x from 0, the first value is equal to the number of your variant. The next one is nv plus 1, then nv plus 2, plus 3, and plus 4. Totally 5 values, and it will be concrete numbers in each case. And also the interval of discretization that is indicated by the capital letter T is calculated like 1 over NV. Your NV is the number of a variant, milliseconds. And your task is to find Fourier image that is marked as capital letter X from K. So X from N is original function, and X capital from K is the discrete Fourier spectrum of this function. And to find this spectrum, you should use the formula of direct discrete Fourier transform, or also we use acronym DFT, discrete Fourier transform, DFT. And this spectrum will consist of the same number of digits. So if we have had original functions that consist of 5 values, then the spectrum will also have 5 values. If original function is consist of 10 or 1,000 or 100 numbers, the same numbers of digits will be in the spectrum. So it's always the same. And here we have a separate component of the spectrum, x capital from 0, x capital from 1, from 2, from 3, and from 4. That is what you need to calculate. And how to do it, how to calculate this, you need to use the formula for the direct discrete Fourier transform. Actually, this formula is already in the presentation that we had in our Google Classroom. But also it is repeated here for the convenience. This notation F with the lower index D means that there is a discrete Fourier transform, discrete because we have a lower index D. And here in the brackets, it could be a figure brackets or rectangular brackets. It's a different notation, but they mean the same. So there is an original function to which we apply method of discrete Fourier transform. So there is just a symbolic notation, and then after the equality sign, we have a formula that you should directly apply. So here we have a sum from n small that is changing from 0 till n capital minus 1. And in our case, in this task, n capital is equal to 5. We already defined this. So your sum will be from 0 till 5 minus 1, so till 4. And under the sum, we have x from nt. So this is these digits, discrete values of your initial function that depending of your number of variant. So you should put it here. And then you have exponents e in the power minus I, k, omega, n small, and t. Here I is the complex unity. And then k is a value that is that doesn't change, because you see the left part of this equation is x from k. So k is like fixed values, and you will do it consequently, putting k equal to 0, then 1, then 2, then 3, and then at least 4. Totally 5 values. So for each of them, you should fix this value and then changing n from 0 till 4 and putting the proper digit of original function here and the proper values n here. And as regards to this capital Greek letter omega, so omega could be found using this formula, omega equal to 2p over n capital T. N capital is again equal to 5, and T is a period of discretization. You have it also depending on your number of variants, right? Here. So you can find omega, and then you put everything here in a sum, and you obtain 5 different values of the spectrum components. And these values could be, in general case, a complex values because we have a complex unity here. So only if k will be equal to 0, here we will obtain e exponent in a power 0, so it will not be complex value, it will be just an integer number. But for all other, in general case, it would be, or each component of the spectrum will be a complex value. So your task is to calculate each of them and to write down x capital from 0, from 1, from 2, from 3, and from 4. This is the first part of the task, and the second part is to draw the graphs. So like almost always, we have 2 parts in each practical task. It's a calculation part and also the graphical part. So the graphical part here is to draw graphs of the x capital K from K. And here you should put K equal to different from 0 till 10, but I think it's not necessary. Oh, now I should correct this. Okay, I will open it here. I have it here. And I think I will correct this because I don't see the sense to do it for k equal to from 0 till 10. So let's do it for k equal to 0, 1, and so on, and -1. In your case, it will be till 4. Okay. Let's put it here. So for one axis, you have components of your spectrum, and for another axis, you have like a counter k that is equal to it's changing from 0 till n-1, so till 4. Okay. I will repeat it here also. There. Here. And one more time here. And k, small k, because this is counter. Changing to capital automatically. Okay. Yeah. So the first graph is the component of the spectrum that you already calculated. But if it will be a complex value, yeah, and it could be complex value because we have a complex unity here, I. So you will not be able to draw this graph because how you would put the complex value on this coordinate plate. So it's necessary to do like a model. Let's do it like here. Model x from k. So if you have a complex value, I suppose that you are able to calculate a model. Yeah. So if you have a real part and imaginary part, so the module could be calculated as a square root from the real part in a square plus imaginary part in a square. Is it understandable? Yes? No?
Doctor, can you repeat again the last part?
Okay. I repeat, and I will I will type it here. So if x from k for certain k becomes complex value, and it could be, then you should calculate the module of this complex number. So if you have complex x from k, then you have to calculate the module of x from k. And how to calculate the module of the complex value? Do you know this? If x from k is some real part plus complex unity multiplied by imaginary part, then how to calculate the module? Who can explain me? I think someone is Zitar meeting. Only Robert is here, yes, right? Robert?
Yes, teacher, I'm here.
Okay. So could you understand how to calculate the module of a complex value?
Can you repeat again, but only the last part?
Like here.
Yes, exactly.
So it will be real part in a square plus imaginary part in a square, right?
Okay.
Like here. So you calculate x from k. You calculate x from k, and you see that this is complex number, and then you have to find the module of this complex number and draw the graph of dependence of the module x from k from the k. Okay.
Okay.
Ahmed is joining. Okay. I will put Ahmed, are you with us?
Yes, doctor. I'm sorry, I lost internet.
Okay, so I will repeat. If we obtain our component of the spectrum in a complex form, so if for certain k you see that you obtain a complex value, then you have to calculate the module of this complex value. And the module you can calculate using this. I'm not writing him like an equation, but I just write down it like a text. Square root of this expression. Okay.
Okay.
And you calculate these 5 values and put it on the graph here. For k equal to 0, 1, 2, 3, and 4. Then you do the same, but for not for model, but for the phase. Because if you have complex value, then this complex value could be represented also by the phase. And this phase is noted by the phi from k here. And how to put it here? Let's see, maybe here. If I will repeat, if x from k for certain k becomes complex value, then you should calculate. This is the same text that we need here. Then you should calculate the phase of this complex number. X from k. This draw below here. So if you have a complex value, then you calculate at first module and put it on the first graph, and then calculate the phase. And this phase could be calculated like phi. I am just writing him not like a symbol, but phi. You will understand that phi, it's a phi, yeah? Phi from k equal to arc tangents of the ratio imagined part divided by real part of the complex number that you obtain. So this is that you need to calculate values that will be put on the second graph. Here for the first one and here for the second. Now let's make our graph a little bit more beautiful. Like here. So for k equal to 0, 1, 2, 3, and 4, you should put 5 numbers of the phase here on the graph number 2. If you obtain not complex value, but the value that is equal, for example, 0, not complex, not real part, not imagined, just 0. Actually, it means that the phase is not defined here because you cannot divide 0 by 0. Yeah, it's uncertainty. It's understandable and unpredictable result. So for the value, and you in any case you will obtain 0 when k will be equal to 0. So if you put k equal to 0 here in the exponent, in the power of exponent, you will obtain 1. But if it's somewhere you will obtain the result, some component of the spectrum that is equal to 0. So the phase for this 0 number will be undefined, and you should just indicate this, that this phase for this k, for this value is undefined. And okay, and the third graph is that you have to draw is a graph of original function. This is the simplest because you have original function in the beginning. Here is your original function, x from n, and it is consist of 5 values that are depending of your number variant. So you just your task is just to put these 5 integer values onto the graph. That's all. But it is not always the all task. The next what you have to do is find the value x k from k plus n for every of k 0, 1, 2, and 3. And you should compare it with the value xk. A little explanation here. Tip. X from k plus 1 should be obtained the same as x from k. So it should be x from k plus n equal to x from k. This is a tip. But you should prove this. You should verify this. We'll do it like here. So for the k equal to 0, you will obtain x from 0 plus n. And your n is equal to 5, so it's in your case it will be equal x from 5. You should put instead k, you should put 5 in the formula that you have here. So here in this formula you should put x from 5 instead k, and you should prove should be equal to x0 if you will calculate everything correctly. The same for the k equal to 1. Then x from 1 plus n, it will be the same like x from 6, and you should put 6 instead k in a formula above, and it should be equal to x from 1, but you should verify this. For k equal to 2, for k equal to 3, and at least for k, that's all. For every k 0, 1, 2, and 3, that's all. So you should do this, and you should see that you will obtain the same like you already obtained, so the component of the spectrum here. Okay, so now this file with for the practical task number 2 is updated, and I will upload this updated file into Google Classroom. Do you have any question concerning this?
No, Dr. Speckley.
Okay, so
No,
you
no.
will try to do it by yourself for your variant, right?
Yes, we'll try to.
Okay, super. And then we can go further, and also in a Google Classroom we have practical task number 3. And now we will see what you should do here in the practical task number 3. Just I'm opening it. All the instructions are in the file attached. You have 5 points to earn for this practical task, and the instruction is in a file. Here, let's open it and have a look. This practical task is devoted to the spectral transform of Walsh and Adamar that we already considered, and that are already in a presentation uploaded to Google Classroom. But anyway, all necessary information for the calculation is here in the file named practical task number 3. So again, the same numbers of the variant, they are constant for all practical work. So for Ahmed 1, for Esteban 2, for the Robert 3. And we have here some initial sequence that we would analyze. This initial sequence consists of 8 discrete values. So our n, the number of discrete digits, is equal to 8. And these 8 values are depending on the number of your variant. NV, 5 NV, 10 NV, and so on. So you should put your number of variant here, and you will obtain initial sequence, just your individual initial sequence that you have to analyze. What you have to do, there are 2 parts of this task. First one is Walsh transform, and the second is Hadamard transform. We already considered it. If you will have some question, you will ask me. But anyway, the calculation are not so difficult. I would say that they are really easy, but you have to do it in matrix form. So your task is to find an image xk with a lower index Walsh for Walsh transform. So you have to use Walsh transform, and in order to do this, you have to use a matrix with a dimension 8 by 8, because you have an initial function that consists of the 8 values. That's why you have to use only one dimension of matrix, 8 by 8. You cannot use any other matrix with another dimension, only this. And here already there is a Walsh matrix 8 by 8, so no problem just to calculate it. I say not problem, but I would like also to show you how to do this. And for this, I would go to the presentation uploaded to Google Classroom. Here there is a presentation number 3, Walsh transform and Hadamard transform, you can see, and I'm looking for the example. Here, example number 1, you can see the only difference of the example number 1 and the practical task number 3 that I'm explaining to you right now is the dimension, because here in example number 1, initial sequence consists of only 4 values. That's why the matrix that is used here in example has a dimension 4 by 4. But in your practical task, your initial sequence consists of 8 values. That's why you need to use the matrix 8 by 8. So you have it here. But anyway, the rest is the same. The calculation is absolutely similar. So you have a matrix here in example 4 by 4. The matrix consists only of 1s and -1, and you have to find the spectrum. Here there is a formula of direct wave Walsh transform. X from k equal to 1/4 here in example, but in your example it will be 1/n, and your n is equal to 8. So you have to put the multiplier 1/8 here, then you should put your initial function x from n, and then the matrix. So in your case, it will be like here, but it will be x from k equal to 1/8, then your initial sequence, and then the matrix 8 by 8. And you should calculate, you should multiply this horizontal row by this matrix, square matrix, and you will obtain again the horizontal row. And here there is a result that is separately written each component of the spectrum, because we have a common multiplier 1/4. Then we can multiply it step by step by first component 6, and we will obtain 1.5, then 0, then 2/4, it 0.5, and then -1. In your case, it will be not 4, but 8 values of the spectrum. And that's all. You obtain the spectrum. And the second is you have to do the same, but using another matrix. It would be transform of the Hadamard, and the only difference between Walsh and Hadamard transform is the matrices. I explained to you that these matrices are very similar. They have the same dimensions. For example, here 8 by 8, but in other cases it could be 4 by 4 or 16 by 16 and so on. But the order of horizontal rows in the matrices are different compared with for Hadamard compared with Walsh, or for Walsh compared with Hadamard. So even here you can compare the visual look of first and second matrix, and you will see that, for example, the first horizontal row is always the same. It consists only of ones, positive ones, but others are just mixed. And in presentation last time, I explained you why they are mixing and what are the law of this mixing. But for the practical task, actually, you don't need this. You have just to use this matrix. So you have to do the same. You take the original initial sequence here. It is the same initial sequence for Walsh transform and for Hadamard transform. And then you do it like in example. So 1 over 8 in your case, not 1 over 4 here. Then your initial sequence, and then the matrix. And the results will be components of the spectrum that the set of these components will be the same, but the order of components will be different for Walsh and Hadamard. And couple graphs that you should to build. The first one is you have to build a graph of the set of Walsh function. And it is very easy to do by taking this matrix, because you have this matrix, and each horizontal row of this matrix, this is a separate Walsh basic function. So you have just to draw the graph for every row. 1, 1, 1, 1, 1, 8 ones, then 1, 1, 1, 1, minus 1, minus 1, minus 1, minus 1, and so on. So it will be like a set of the graphs, and also it could be something like, I will show you, something like this. There is, and the slide in this presentation number 3, you can see the set of Walsh function. You should do the same in your practical work. So just to draw this set of Walsh basic functions for all of your case, so totally 8 values, 8 functions, and then the set of Hadamard functions. And to do this, you have to take a Hadamard matrix. The functions will be the same, but the order of this function will be different. So the same set, but with another order of the function inside. And also you have to put on the graph image of that you calculated in a first part, Walsh image that you used, where you used the Walsh matrix, and then image the spectrum of the Hadamard that you calculated using the second matrix. So that's all. That's it for the practical task number 3. And also, I believe that it is not so difficult, but anyway, again, if you will meet some difficulties or something will not be clear, you can ask me. Would you like to ask some question right now?
No, Doctor, right now, no.
Okay, so what I will do, I will update the file for the practical work number 2, because I added something for the explanation during our meeting, and actually I will do it right now after our meeting. And for the practical work number 3, everything okay, so you can just start your calculation and if something will not be successful, you will inform me, but I believe that everything will be okay. Okay, so I think it would be enough for the moment, because after this we will go to the next topic of our lection materials, and I don't want to mix them. So I would prefer that you at first finished everything with practical task number 2 and number 3, and then we will go further, if you don't mind.
Yes, doctor, yes. Yes, okay.
Okay, so that's all for today. And also I will upload recording
Okay, thank you very much.
if necessary. Okay, have a nice rest of day, evening or day, or for different time zones will be different. And thank you for the attention. See
Okay,
you.
doctor. Have a good
Thank you,
evening.
Teacher Lisa. Goodbye.
Bye.
Goodbye. Goodbye.